Problem number 15 is asking us to apply root test to a series and see if it converges absolutely, diverges, or is inconclusive. So the series is summation from n equals 1 to infinity of 1 minus 1 over n to the n squared power. So let's go ahead and apply root test and see what we get. So L is equal to the limit as n approaches infinity of the nth root of the absolute value of a sub n, where a sub n is just the term inside of the series. So if I go ahead and apply that, I end up getting the limit as n approaches infinity of the absolute value of a sub n is just itself. There's no negative term, there's no alternating term that we have to get rid of in this case. So I end up getting 1 minus 1 over n to the n squared, and by taking an nth root, what that really means is I'm taking the whole thing to a 1 over n power, so I'm going to divide this by n. What that leaves me with in this case is that leaves me with the limit as n approaches infinity of 1 minus 1 over n to the n power. Now, there is a shortcut for this limit. It actually converges to e to the negative 1, but let's go ahead and try to prove that out. So if I try to plug in n as n approaches infinity, I end up getting 1 minus 1 over infinity, that's 1 minus 0, to the infinity. So 1 to the infinity is an indeterminate form, so that doesn't tell us anything. However, when it's indeterminate, we can apply L'Hopital's rule if we can get it into a fractional form. So what I'm going to do is I'm going to end up taking the natural log of both sides. So lny is equal to the natural log of 1 minus 1 over n times n out front. So again, when I take the natural log of something, I can bring it down in front. And also don't forget, we're still taking the limit as n approaches infinity. But first off, we have to get it into a form where we can apply L'Hopital's rule to that before we can do that. So I'm going to bring this n down as a 1 over n power. So I end up getting natural log of y is equal to the limit as n approaches infinity of natural log of 1 minus 1 over n to the 1 over n. Now it's in a fractional form and it was indeterminate, so we can apply L'Hopital's rule to it. So if I derive the top and I derive the bottom, I end up getting lny is equal to the limit as n approaches infinity of, so derivative of natural log is u prime over u, so it's the derivative of what's inside over the original term itself. The derivative of negative 1 over n squared is positive 1 over n squared. Or sorry, the derivative of 1 minus 1 over n is positive 1 over n squared. So I end up getting that over 1 minus 1 over n, and then on the bottom, if I derive this out, I actually end up getting negative 1 over n squared. So these terms and this term can cancel, so I'm left with an extra negative out front, so I have limit as n approaches infinity of negative 1 over 1 minus 1 over n. If I take the limit of this as n approaches infinity, it's no longer indeterminate, so I can actually evaluate it. 1 over infinity goes to 0, so I'm left with negative 1. However, I took the natural log initially, so I need to raise both sides to an e power to get it back to its original form. So therefore, y is equal to e to the negative 1 in this case. So what that means is my L value, after I take the limit of this as n approaches infinity, should equal e to the negative 1. Now, thinking back to the rules of root test, it says that if L is less than 1, it converges absolutely. So 1 over e is in fact less than 1. It's a fraction. E is about 2.72. So 1 over 2.72 is definitely less than 1. So therefore, the series should converge absolutely, which means that the answer has to be B.
The Teaching Center, UF's Learning Resource Center.